Lecture number 7, E512 CMOS analog IC design. And today is September 9, 2023. So I was looking at the previous, that, where is that now? So this is, there was a problem. It was equation for resistance only. Somebody was from here asking. The previous slide, this one, here resistance was missed. That is what we found out actually. R1 was correct. That was the thing first. Okay, so now let's talk about various second order effects which are not actually given in the square law equation. If you remember, the square law equation is as follows. It's ID mu n C ox by 2 W by M VGS minus VT square. Right? So this is a square law equation. It's an approximated one. It has lots of things. If you are including many other second order effects, by the way, why we are calling it second order effects or higher order effects? What is the meaning of that? What is the meaning of this? Because that is the title of the next slide, second order effect. But why it is second order? The second power is here. So generally, this is very general term, by the way. It is true for any subject anywhere. Yes, true. But why second order, or what is the meaning of this higher order or second order effects?
Number of approximations are less. Number of approximations are less.
In second order, number of approximations are still there. So if you know, this is a linear system. But in reality, these are the things, right? Let's go this way. So this is second order, third order, and so on and so forth, right? Fundamental, second harmonic, third harmonic. So if you are writing an equation where you are approximating that to the first order only, that's the linear equation. So that is the simplest one. If you are adding many more things like second order, third order, and so on and so forth, you will see many more effects. But we are, restricting ourselves to second order or third order effects only. Later on, there is not much problem, right? So that's the actual reason behind that. If you want to understand, if this is the signal A sin omega t, can you draw its equivalent in frequency domain? Draw that in your frequency domain. How does it look, Narvik? Very simple, right? So let's call this one as omega 1. You are expecting at omega 1, what you are expecting? What about minus omega 1? And what's the value? Right? A by 2j, right? Minus a by 2j, right? From the equation, right? We can say. But we are not interested in such kind of things. We are interested in only positive things. Let's forget about other things. If it is going through an amplifier whose gain is 10, what are you expecting? Only this one. Let's make it mod of that one. amplification times, let's call this one as alpha times the amplitude. This is what are you going to see through this amplifier or something else. The amplifier is made up of MOSFETs, which is itself is non-linear device, right? It's not a linear device, it's a non-linear device. So what do you expect? It must have, second harmonic, third harmonic, because that's the science, right? As per the science or the theory of Leonardo da Vinci, this will give you all the harmonics from fundamental, second harmonic, third harmonic, so on and so forth, with some amplitude, and that's how it's going to give you something called signal to noise ratio, SNR, and many things are there. Total harmonic distortion. That's the next level of this course, which is generally we are studying in mixed signal VLSI design. My point is, when you are interested to see many more things, right, then you have to include the higher order effects to get the exact answer, right? So as much you are taking that much good answer you will get. Anyway, so this is one of the second order effect. Still there are many higher order effects are there, but we are only including few second order effects which are going to give you second approximation, right? So if this is an NMOS, and you can see there are two red boxes are there, right? So it has some overlap. Because of overlap, you might have, instead of having equation which was like this, you might have the case that it might be L prime. Like one of the place it was written it's an L prime, right? So here I am saying, if I am considering L, the new equation will be 1 plus lambda VDS. This is similar theory which we have used for maybe BJT, where you have the early effect, right? With E is capital, by the way. Do not keep E in small letter. You know why? He is a scientist, right? Early is the name of the scientist. Like when I used to study, I searched about what is early and why people are not writing in small letter. Later on, I realized it's the name of the scientist. That's why early effect. It's in BJT. Its similar effect is here in MOSFET, known as channel length modulation, where channel has actually overlap and actual channel length becomes L prime, or you can say even if it's L, some delta L you are going to observe. Extra delta L is there. That delta L by L I am going to call as lambda VDS. That's the unit of that one. Okay. Just for matching, you can understand lambda might have, what should be the unit of lambda, by the way? Volt inverse, right? Just to match all the dimensions, you can find out lambda has to be volt inverse, right? Because delta L by L is actually unitless, so it has to be volt inverse, right? And this is the equation. This is with the philosophy that it is similar thing which is happening in early effect voltage also, that you are expecting to have equation like this, where there is no role of VDS at all when you are in saturation. So this point is actually VDS set is equal to VGS minus VTH. Okay, this point, this dotted line is actually distinguished between two different regions. One is linear oblique triode and other side is saturation. Note that if you are in BJT, the characteristic will have, this will be IC with respect to VCE, and this red line will be here, and both sides the names will be different. This side, what is the name? It's an active mode. And note that sometimes people ask such things in interview, just to make sure that whether you know BJT or not, but saturation is here. There, right? So let's not make such mistake. I just told so that you remember it and you don't make mistake. Right? So IDS versus VDS. So it is expected that in saturation this equation holds. In this triode region, the equation is different. What is the equation? VDS minus VDS square by 2, right? So that two equations are there. They are distinguished by one single line. When you are in saturation, that becomes, your VGS is more than 2 5 here. So that's the equation. It's a device equation. No need to remember it. But you are going to have this kind of characteristic. So this is a flat. This is, the slope of this line is 0 right now because there is no relation between IDS and VDS at all. So it has to be 0. Del ID by del VDS is 0. That's how this is flat. However, in the presence of channel and modulation, in reality, you are going to see something like this. Some slope might be there for a different value of VGS, by the way. Okay. So VGS values are increasing for different values of VGS. This is what going to happen, and you will experience some slope over here. In the presence of slope, this is the equation, and that is also the thing that the beauty of this device is it is meeting one point only. Right? It has some value. Let's call it VA or something. No problem. Right? But it meets only at one point. So this is what happening similar to BJT, but this is the channel and modulation, and that changes the equation. Again, I am not going into derivation of this. This is device derivation, right? So now remember this equation in the presence of channel and modulation. So when there is a channel and modulation, where lambda is delta L by L by VDS, that's lambda, right? Or delta L by L is equal to lambda VDS, right? So this is what is happening over here, right? And whenever you are going to take del ID by del VDS, that is going to give you 1 by the value of resistance. Some people call it RDS. Look, it's small letter R and DS, right? So you can call it RDS. You can also call it RO. Different books are following different notations. Both are same notation. If you are seeing RO, if you are seeing RDS, both are channel and modulation resistance. Okay, so do not get confused with different notation. So RDS is a common notation in Behzad Razavi book, blue colored book from where I have taken, and RO is actually from different books like Alan Holberg and many other books. They are using RO, right? Some people are also reading this at R0 also, even though it's O. O stands for output resistance, by the way. That is how they are saying. So both are same, but it is notation wise it's small letter, so do not make mistake. However, if it is R on, what is the name of this resistance? R on? Yeah, so it's on resistance when transistor is in triode, right, or in linear. So do not get confused with this. And del ID by del VDS is equal to RO or RDS. So what will be the value of that one? Can you find out that? Sorry, 1 by R. Okay, 1 by R. 1 by lambda ID, right? That's also the correct one, right? If you solve it, you will see that 1 by RO is equal to 1 by lambda ID. So that's the answer for this one. Okay, so you can keep it somewhere in your mind. This is simpler one. R0 is nothing but 1 by lambda IT. Should I go forward? Hmm? It's fine, right? Okay, so R0 is 1 by lambda RD. That's the equation, right? Okay, so now the work is for you, that you need to find out the two-port equivalent model when there is channel and modulation. Understand? Earlier we found out with this equation, we found out where there were no availability of VDS. However, in this case we have extra VDS is available. So in that particular derivation, we made all del ID by del VDS goes to 0. Right? When it's in saturation, following the square law equation. But when it is not square law equation, if it is with channel and modulation, then can you find out what is the small signal model? You can use two-port network, which we have studied last time, right? One extra thing will be coming, del ID by del VDS, that's RDS. That has to be here, right? So now can you tell me different resistance looking into different ports? So gate resistance is infinity, source resistance is 1 by GM in shunt with RDS. See? Looking from drain, RDS. Note that now, remember it, 1 by GM is in the range of few ohms, hundreds of ohms, right? RDS is generally more than 1 kilo ohm. So in that case, I can approximate this to 1 by GM. That I can consider as low. RDS is 1 kilo ohm, I can consider that as high, and infinity is obviously high. So input resistance is infinity, output resistance is also infinity. So still this qualifies as voltage controlled current source, or it acts as an OTA, or the operational transconductance amplifier, or I would say, if you like, it's only transconductance amplifier. Okay, so moving to the next thing is, by the way, any problem in channel and modulation? Right? So channel and modulation happens most of the cases. You can't neglect it. So please do not neglect this channel and modulation resistance. Right? In the current era of where very subthreshold, uh, sorry, deep submicron technologies are there, where you are going in 3 nanometer. So of course, it's very difficult to make exactly 3 nanometer. Nobody can guarantee that, right? Even to give the guarantee of 180 nanometer is also difficult, right? There will be something extra. So that's why we call this particular, channel and modulation is exist, and we are going to use this as the small signal model. So this is a small signal model. Understand one fact, that when it's a small signal model, you are running the whole thing at low frequency. That's why there are no capacitances right now. We are going to talk about high frequency model where capacitance will be there. And we already talked that parasitic capacitances do exist at very high frequency. And also small signal is dealing with the small amplitude of the signal. That we also know what is small amplitude means, right? It's not getting saturated at the output, that's the small amplitude, right? So accordingly you can find out the what is the small amplitude and what is the low frequency, right?
So the CLM at channel and modulation are due to diffuser length or due to pinch off.
What do you think? It's not because of pinch off. Pinch off and other things are the secondary thing. I'm talking about the geometry, right? I'm not talking about the device physics.
But it dependent on BTS.
That's a different thing. Can you see the overlap? I'm showing you the geometrically. There is, can you see directly the drain voltage? Drain is also affecting the current. Earlier it was like this, right? Drain and source didn't have any control over the channel. Understand? Gate was only controlling channel. Now it's not the case. You see the possibility that drain and source voltage will also interfere, and that's what happening, right? Okay. So if you understand that, then there is no problem. Let's go to the next thing, which is where you should connect the body. By the way, body is also having various names. So substrate, bulk, anything which you like, you can call it, right? Different book authors are writing in a different way, right? So any one of them is fine, no problem. So biasing means the DC quantity available at a respective terminal to make the desired operation of the region, right? So this is required, and it is very important that you connect body somewhere. So if it is an NMOS, actually it's a 4-terminal device, not a 3-terminal device, unlike BJT, where you have gate, drain, and source, and this is a body. So generally, we like to connect body with the source, is irrespective of what device you are using. So either you are using NMOS or PMOS, we generally like to connect body and source together. We already talked about this one, where I told there is one equation where threshold voltage may vary. So VTS 0 is the one which is given in the DRM, which is design rule manual, and gamma is the body effect, phi f is the Fermi potential. So body effect coefficient. This is body effect coefficient. This is also model parameter, by the way. Phi f is Fermi potential. So if I make VSB equal to 0, then and then VTS is equal to VTS 0. If I want to have VTH and VTS 0 exactly same, then I need to make VSB equal to 0. That is the only possible way, right? So the best thing is to connect body and source together, right? But there are many problems in this case also, that if source is not connected to ground or not connected to VD, then there might problem that if source is, let's say, connected to somewhere else, let's assume that if I am connecting this to some sine wave, this is possible, right? I can do that. If it is changing, then body is also having sine wave as an input. So there are two inputs are going for simultaneously to the device, and this device not only work as a common gate amplifier, but it also work as, you know, the some other amplifier which is actually giving you the amplification from the body. If you look at that equation, so what exactly will happen in reality? Body is also designed such a way that input resistance is infinite, and you are going to see this one. However, it will also give current like this. The way gate was controlling the, you know, dependent current source, same way body is giving you some dependent current source which is going to give you GMB times VBS. So this will happen if your connecting sign here, sign is also here, right? So, or if body is moving somewhere, same you can observe over here. So this is the second order effect, where you are not connecting body with source. If you are not connecting body with source, or body and source are not tied together, if this is not the case, then you will see some extra current over here. So that's the body effect. When body potential is not equal to source potential. Or VB is not equal to VS, then body effect will be there. Otherwise, no body effect. You don't have to consider this GMB times VBS. By the way, GMB is another transconductance offered from the body. Okay, so that's why we made this one GMB. Some books they like GMBS, body and source together. Right? So any of the notation, both are again same. Different books are following different notation. Our book Razavi is following GMB. Right? All these things happen because of two different, world, like American people and non-Americans, right? So they don't like the units of other people. Right? They use their own units. We like kilometers, they like miles. Right? We like liters, they like pounds. So similarly, they change everything. So they also change body to substrate or bulk, GMB to GMBS, and so on and so forth. Okay, so depends on whom you are reading. If you are reading American people, so GMBS is possibility that it will be there, or different notation they are using. Anyway, okay. Okay, this is already done, right? So we are not going into this. Okay. Why it is same? Okay, by mistake, same slides kept. Okay. So now there is another thing which is subthreshold conduction. So subthreshold conduction is the one we assume that below VTH voltage, gate source voltage, uh, at gate source voltage, the transistor is turned off. But that's not true, right? If you've seen VGS versus ID characteristic, you will see that if this is VTH or the threshold voltage, before that itself you can observe some current is flowing, right? Or you can take the tangent over here, and whatever is there, that you can call, let's say, VTH. On that you can call it VTH2, somewhere like this. In between there is actually conduction, so that is subthreshold conduction, or you can say that from weak inversion to strong inversion, that particular region is actually subthreshold conduction. It is also written here, transistor on in the weak inversion is called subthreshold conduction of the transistor. Right? Both the sentences copied from Behzad Razavi. Right? So subthreshold conduction is sometimes dangerous also. So the transistor can give you amplification. Right? You wanted to keep it off, but it's not off. It can act as a switch even if you don't want that to be on. Right? So that's why sometimes we need to check the subthreshold conduction whether it is there or not, because it might happen that your circuit work at TT. You know TT? Typical corner, right? It can work at typical corner as you want it, but maybe at slow, fast, and it's a combination of NMOS and PMOS, or maybe FNSP or slow fast, right? In that it might happen that one of the transistor, instead of having in saturation, went to subthreshold, or cut off to subthreshold. So it will change the whole thing. That can reduce your gain. even if it's like expected to be in saturation, but now it's in subthreshold. So what will happen? The overall GM will decrease, and that will give you lower amplification compared to the previous one. That generally happen on at slow slope. Right? And similarly, for if you are using as a switch, you are expecting that to be in cutoff, but now if it is in subthreshold, it might happen that it can give you, the required connection between input and output, and it can give you the wrong result, right? So those are the things. That's why subthreshold is very important. This happens mainly in circuits like biomedical, where you are keeping very big size of WL. This happens. So you have to design it such a way that it works at PVT. Look, it's a your own jugaad technique. You have to find out. PVT, nobody will teach you how to do it. Everybody has to find out their own way, own tuning techniques, right? So it might happen that at TT everything works fine, but to maybe at one corner it's not giving the expected result, or at 6 sigma it's failing. So how to tune it? You have to find out, because it's also an art. If you are touching something, it might happen that instead of one corner, almost like 100 corners it's failed. If you're correcting one corner, this will happen, and that's why people are spending lots of time in industry for designing a single op amp, right? But that's the whole course about. If you know op amp, believe me, you can go outside and you can say that you know something about analog. Until you do not know how to design op amp, you should not claim that you know analog at all. Until that time, it's just useless for industry. They need at least someone who understands op amp over the PVT, by the way. Right? Even if you don't know layout, that's fine. This is what they want, and you have separate layout engineer in company, right? So that is what there. That is what for subthreshold, right? So the subthreshold conduction current can be measured from the transistor from weak inversion to the strong inversion, right? Observed for ID versus VGS curve. So you can observe that through that curve. It is similar phenomena seen in BJT when observed IC versus VBA curve. This is also same name, everything is same. There also subthreshold conduction stays there, and many a time we are, by the way, we are talking about little bit of BJT because you can't get rid of BJT. Okay, if you forgot, please try to learn that also along with MOSFET, because some people who wants to go for RFIC design. This is also one higher level course beyond analog, which is for radio frequency integrated circuit, where you can't get rid of BJT. Still, in your mobile phone, power amplifiers and many other things are made up of BJT, and that's why BJTs are still important. It's not completely vanished. Still, MOSFET is and BJT both are there. Without that, you can't do that because it has very high current gain. Beta factor is quite high. Right? So anyway, so this is about subthreshold conduction. Right? If you draw VGS with respect to log of ID, earlier it was like this. Right? Now, if you take log of ID with respect to this one, you can see that this particular region, which is following the square law, having the equation of whatever the ID is equal to mu n C ox by 2 W by L, VGS minus VGS square. And here, ID and VGS equation is also exists, and this is called subthreshold conduction slope. So this particular term is very important in all device engineer. Subthreshold conduction slope. So you should have very good high subthreshold conduction slope, so that device is qualified as a good device. That's the thing. So generally, this is the number given for some bigger technology node, like something like 180 nanometer or maybe a little bit bigger of that. Anyway, so now this is the summary of what exactly we have studied till now. The transistor can act as a resistor, when you are keeping that in triode or linear region. And when you make, partial derivative of IDS with respect to VDS, the value which you are getting is R on with the subscript of on, R on. So this is the first thing. No problem, no doubt, right? And this is the thing which we are going to use it for all digital circuits also. So use the equation of ID, this one. Right? This is for triode region, a linear region. However, if you are interested to make your transistor in amplification mode, which is true for saturation mode of operation, in that case, a transistor provides transconductance current when transistor operated in a saturation region, and that will follow this equation. If you solve this, you will find out GM. So GM is important term, as first thing was R on was very important. Same way, second is GM is important without having anything else. If it is GMB or GMBS, that's the body effect based transconductance. But normal GM can be found out by the square law equation, and that's del ID by del VGS, and that's going to give me the value, right? And what is that value? Sorry, muon Cox W by L VGS minus VGS, right? This is very simple. Right? There are various ways to write down this. We will talk about this later, but this is one of the equations. This has lots of trick, by the way. So this is second one that you are finding out GM. So first one was R on, second is GM. Third one is actually channel and modulation, which you found out, or known as RDS or RO. So RDS or RO can be found out by this equation 1 by lambda IDS, right? You can take the derivative del ID with respect to del VDS. That's going to give you the channel and modulation resistance. That's the third thing. And the fourth thing is actually the body effect. And you can have transconductance current from body. That's GMB or GMBS, whichever you like. You can write down. Anyway, so GMBS is also that, which is flowing from the body to source. And when you are not connecting body with source, this current will be observed. So accordingly, you have to follow the small signal model. So the actual small signal model, including body effect, including channel and modulation, are as follows, right? So that's the complete small signal model, which is at low frequency and with the small amplitude, right? So now, can you tell me what is the resistance looking into gate? It's very simple, right? Looking from body, looking from drain, looking from drain. You might be, oh sorry. So VGS and VBS are at 0, so this is only R0, right? Looking from source. It's same. You wanted to say something 1 by GM plus GMBS, it's same, right? Understand, generally 1 by GM is actually smaller than 1 by GMBS. If it is 100 ohm, then this is around 200 ohm, 300 ohm, 2-3 times, the difference is there. So if you are considering 1 by GM, do not neglect other transconductance. And if your combined effect might be uh, might be comparable with RO, it depends on the technology. However, if you want to approximate it to R0, no problem. Okay. But you have to assume that this entire quantity is much lower than R0. Right? Then and then this will happen. So, sorry. It's a mistake again. Sorry. It has to be 1 by Gm plus Gm. Right? But as I told you, in this particular case, it might happen that 1 by Gm plus GmbS is comparable to R0. So you have to see accordingly. Right? For a smaller technology node, you can't neglect it. However, for book and the derivation purpose, you can neglect it if you want, right? But you have to write down those, the whatever approximation you are making, you have to write down. Okay? Wherever you go, like I'm saying, in companies for any interview, if you go, if you are writing that the source resistance looking from here is 1 by Gm plus GmbS, you won't like it. You have to say that 1 by Gm plus GmbS in shunt with R0. That's the actual number. So tell always the correct thing, not the approximated one. This is what my suggestion is, right, for any interview. Okay. So these are some of the derivation which we have, like. So R on will look like this one, 1 by mu on C of W by L, VGS minus VGS. That has to be the answer, right? When you are here, much lower than 2 VGS minus VGS. That's the region. If you are following this, then you can approximate the current equation as follows. And for that current equation, this is the thing. We are approximating this just to make sure that you are not you are not in this region. You are in the region which is linear. That is the meaning of that. Right? So that's why this will be the answer for that particular R1. That was the first thing. Right? GM is, am I going fast? Because these are very simpler, so that I can go directly amplifier after completing this. That's why I'm going a little bit high, but if you feel it is fast, then let me know. So GM is del ID by del VGS. That's going to give you this equation, mu and C of W by L, VGS minus VGS. So here, this is very important thing, that GM is actually proportional to VGS minus VGS, right? You can write down this somewhere. Or you can say that if there is no body effect, GM is proportional to just gate and source. If source is connected to ground, body is connected to ground, it's only depending on VG, right? Because VDS is already the model parameter, which is equal to VGS 0. So there is no problem. Okay, same equation, but I'm writing in a different way. I can use this, but this equation, I little bit change. I'm calling that as 2 mu on C ox W by L times ID. ID is nothing but same equation. Same equation is there, but written in a different way. If you look at this equation, this is same equation, look alike to this one. We are doing it purposefully just to make sure that GM is becoming, in this case, square root of ID, proportional to square root of ID. Earlier you are saying that GM is proportional to VGS minus VTH. Now you are saying this from this equation is proportional to square root of ID. So this is another thing. Let's keep it there. And the third thing, if you again change it, you will see that it's 2 ID by VGS minus VTH. So this says that GM is proportional to ID and GM is inversely proportional to VGS and VT. Right? So which one is correct? All of them, but
Sir,
which one are you going to follow?
So it depends on the condition whether WL is constant, ID is constant.
That will be constant, right? That's why they are out. In this case, VGS minus VTH is constant, then it's proportional to ID, right? That is fine. In this case, understand what you want to keep it constant. Everything is like mu and Cox are model parameter, W by L are already fixed. That's why it's in square root of ID. So one time we are saying it's square root of ID, and one time we are calling it's proportional to ID. It's depending on you. That's why I told it's a PVT corner and all these things you have to design. Every designers are different. Me as a designer, I am following the third equation sometimes. Okay. Sometimes I change my designing tactic and I go to maybe first equation. With all three equations are correct but with different conditions, and you have to design it accordingly. You have to design it accordingly. When we are going to design, you will understand what exactly I meant. All three equations are correct, but it depending on the designer. I am going to teach with the fact that I am going to teach with the first one, the whole course. With on paper, I am going to use. But some people are following, through this one. This is also one of the popular technique. What I am following is another professor called Professor Sensen from from IMEC Belgium. So he is also like one of the great like analog circuit designers. So his way of designing is the first one. There are many Americans who are following GMID method, right? So it's also another method, right? So there are different methods through which you can design for a given speed, for a given gain, and for different specification. You can choose any one of the technique. Then you will have the whole answer. Designing means op-amp design or amplifier design. I'm saying those techniques and other things are actually limited for analog designing. For the case of digital MOS LSI circuits, it's going to be different, right? Then you don't follow all this because first of all we are following the square law equation. In that you are not going to follow the square law. You are going to follow the triode region equation, right? So you have to follow the R on rather than going into GM. So R on is very very clear, right? It has only one equation. There are no variety, right? So it's simpler one. Yeah. Okay, so you can we will learn about it with time. Right? When you are going into laboratory, you will understand what exactly I meant for. Okay, so there are the various plots as you are saying with some different constants. You can have GM with respect to VGS minus VTH plot is changing. Look at this. Look at this. Right? So equation wise, the plots are also changing. In one of the way, I follow this one because I like it because it's a linear relation. Linear is more easier to have better thing, but still it's depending on the designer. You have to find out your own technique so that it works at PVT. Nobody cares how you make circuit works at PVT, but you have to use some technique because one of the transistors if you are touching, maybe it will disturb many things. So you have to do the things very wisely, right? So those are the things. Maybe we can sign off for today, and maybe next time we can again talk maybe on Tuesday. So that's a completion of one part at least. These are also some of the equations. Maybe let's. So this is also very simpler one by lambda ID. Okay, this is 1 by GMB. So GMB is equal to this equation. That we got it from this equation. I took it from device book. Okay, so we are using it VTH with respect to VTS, and VTH is this one. Same way. GMB is actually, if you're writing it, GMB or GMBS is equal to eta times GM. You can keep this one simpler one. Simple is as follows: R0 is 1 by lambda ID, and GMB is eta times GM, where eta is some number, a plain number 1, 2, 3, 4, some number. As I told you, like GMB is always higher than GM. Okay. So that's all for today.